Welcome to Center of Math's Images in Math. Today we're going to talk a little bit about convex polygon triangulations. So this is just taking a convex polygon. So for example, this is a triangulation. So we just take a convex polygon and draw lines between the vertices. And because it's convex, we can always draw a line between any two vertices, and we split it up into triangles. So it turns out the number of possible triangulations of a polygon with some number of vertices is related to the Catalan number, which we can prove. Before we do that, we're going to prove one other thing. So first, a quick theorem. So for any polygon with n vertices, any triangulation is going to have n minus 2 triangles and n minus 3 diagonals in it. So simple example is a square or any rectangle shaped object. Any triangulation is going to have one diagonal, so between any of the vertices, and two triangles. So n minus 2 triangles and n minus 3 diagonals. So to prove this for any number n, take some polygon. Now first we're going to, so every triangulation clearly has diagonals. We're going to take one of these diagonals, say it's from A to B. And then we're going to look at the number of triangulations and diagonals of, now it's split into two regions, and we're going to look at the triangles and diagonals of each region separately. And we're going to assume, this is going to be via induction, so we're going to assume for every polygon of less than n vertices that this is true. We're going to show it must be true then for a polygon with n vertices. So taking a diagonal for two regions, we have one region with n1 vertices, another region with n2 vertices. So we have n1 plus n2 equals n plus 2. This is because we double count the a and b points, which is the points of the diagonal that they share as a boundary. So note that, so now that we've divided it up into two regions, by our induction hypothesis, the n1 region is going to have n1 minus 2 triangles. The n2 region is going to have n2 minus 2 possible triangles. And so putting this together, we have n1 minus 2 plus n2 minus 2 is n1 plus n2 minus 4. n1 plus n2 is just n plus 2, so this is equal to n minus 2. And so from this, we have that, in fact, there are n minus 2 possible triangulations. Now for the diagonals, we do a similar thing. We note that we have n1 minus 3 diagonals for n1, n2 minus 3 diagonals for n2. And also, this is not including the one diagonal that they share, because this is on the boundary of these two polygons. So n1 minus 3 plus n2 minus 2, minus 3 plus n2 minus 3 plus 1 will give us the total amount of diagonals for a triangulation of n. So from this, summing these two up, we get n1 plus n2 minus 5, and 1 plus n2 is again n plus 2, so n plus 2 minus 5 and n minus 3, and we get again that we have n minus 3 diagonals in our triangulation. So from this, we got that for any n vertices, we must have n minus 2 triangles and n minus 3 diagonals from our induction. So to count the number of possible triangulations, we're going to use a procedure where we contract an edge of a polygon. So say we have some polygon with n plus 2 vertices. We're going to map a triangulation, every triangulation of n plus 2 vertices, to a triangulation of n plus 1 vertices. So we're going to do this by contracting one of the edges. So say we have one of the edges, we kind of bring together the 2 points and bring together all their edges. And so if we bring this together, it turns into this image. And so now we want to know, given this image and given a verse that we're going to unexpand, how many different polygons with n plus 2 vertices correspond to when we map them to an image given a triangulation in n plus 1 vertices. So it turns out, so the number of possible triangulations corresponding to contracting triangulation here to to get the image here, and assuming we're a certain point is the point that's being contracted to. So it's equal to the degree of the vertex. So to see this, note that we picked a point. We're going to say we're going to expand around that point. Each edge of that vertex can open up into a triangle. So once we kind of expand that vertex in two vertices, we can pick any one of these edges to then become part of a new triangle. And so this gives us a bijection between the number of edges and the number of triangulations that once we contracted a certain edge, once we picked an edge vertex pair, we would map from one to the other. So using this observation, we can do some summing and we can get a relation, a recursive relation, giving us the number of triangulations for t for n plus 2 given triangulations for n plus 1. So we have the sum degree, so the number of triangulations t n plus 2 equals the sum of the number of possible over every possible triangulation of n plus 1. We're going to pick a vertex, call it vertex 1. So we're partitioning all the possible t's into a corresponding, each of the corresponding triangulations of n plus 1. And for each of these, we look at the degree of vertex 1, and this gives us a partition, the inverse function. For the degree number gives us the amount of triangulations of n plus 2, which map to this t n plus 1. So this sum will give us the number of triangulations for n plus 2, given going through each triangulation of n plus 1. So to make this sum simpler, we're going to sum over each vertex as well. So from n equals 1 to n plus 1, we're summing over each vertex in each triangulation now. And summing through 1 to n plus 1, this just becomes n plus 1 t n plus 2. Switching the sums, now we're summing first over each vertex. So sum of degree vertex I from I equals 1 to n plus 1. So because this polygon has n plus 1 vertices by our previous theorem, we must have n minus 2 diagonals as well as n plus 1 edges. So that's 2n minus 1 possible edges in our polygon. And because we're counting the degree of each vertex, we actually count the edges twice. So this sum becomes 2 times 2n minus 1. And then summing over each triangulation of n plus 1, this is just little t n plus 1, little t n plus 1 being the amount of possible triangulations of an n plus 1 polygon. And so now we have a simple recursion. And by just repeatedly doing the recursion, we get triangulations for n plus 2 equals 2 to the n times 2n minus 1 times 2n minus 3, dot, 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 all the way to 1 over n plus 1, then n plus 2, dot, 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 all the way to 1. So note we can fill in the spaces 2n minus 1, 2n minus 3, the spaces here as 2n, 2n minus 2, etc. This is just 2 to the n times n minus 1 factorial, or n factorial. But yeah, that's just 2 to the n times n factorial, where we have a 2 to the n here. We'll put the n factorial by top and bottom when we get, and take out the n plus 1. And we get this is in fact equal to 1 over n plus 1 to n choose n, which is the Callan number, and the number of triangulations of a polygon. Thanks for watching our Images in Math. If you like this video series, please watch the rest of the videos in the series. Thank you.